Hello friends. So today we are going to do questions from heat and thermodynamics, and questions are from the year 2000, 2001, 2002 and 2003. From 2001 we are having one question. From 2000, sorry, in 2000 we are having one question. From 2001 there are two questions. From 2002 there is one question, and from 2003 there are two questions. So total we are going to solve 6 questions. So first question, it was asked in the year 2000, and it states that 2 moles of ideal monoatomic gas are taken through a cycle ABCA as shown in the PT diagram. During the process AB, pressure and temperature of the gas vary such that PT is constant. If T1 is 300 Kelvin, calculate. So based on this we are having two parts. In the first part we are supposed to find out the work done in the process AB, and part B we have to find out the heat absorbed or released by the gas in each processes, and we have to find out the answer in terms of the R, that is our gas constant. Basic figure, a PT diagram is given to us. So it starts from A, goes to B, then to C, and then back to our A. Okay. So let us start with our AB process, and AB it is given as that our product of pressure and temperature is constant. Okay. And for BC it is basically pressure is constant, and from CA temperature is constant. Okay. So let us start with our AB process. So you can say for AB we are given that the product of pressure and temperature is our constant. Now if we do a partial differentiation of this equation, we can write this as P of dt plus T derivative of P is equal to 0. Okay. And now we are going to make use of rather the partial differential, not partial but ideal gas equation, and we can say that for ideal gas equation we know that our PV is equal to nRT, and it is having 2 moles, so substituting value of n as 2, so we get this as 2RT. Okay. And in terms of pressure we can write this equation that our P is equal to 2RT divided by V. Okay. And or let me write it as it is. We have to do it. Okay, let us keep it as it is. That is going to help us. So we can write this as our PV is equal to our 2RT. And we are also going to do partial differentiation of this equation. So this is going to give us P derivative of V plus V derivative of P is equal to our 2R is our constant, and then comes our derivative of T. Okay, and V so let us call this as equation number 1 and equation number 2. Okay. Then from our we can make use, let me write this as our P is equal to, this comes as our 2RT divided by V, and if we can use this into the first equation, so we can say from equation 1, we substitute this P, we get this as our 2RT divided by V, and this is our dt, and plus T derivative of P is equal to 0. And we can just sort it out a little bit, and this will be giving us as 2RT dt plus V multiplied by T derivative of P is equal to 0. And we basically here V, because we can take T as common, so obviously that is not equal to 0. So from here we can write that as our 2R dt we can either 2RT dt is equal to, this comes as our minus Vt dp, and we can write this as other way around also. So we can say that our Vdp is equal to Vdp will be equal to our minus 2R, and we have this as d of t. Okay. And now we can use our equation number 2 and substitute this as our in place of Vdp. So we can say from equation 2, we can write this as our Pdv, and this will be coming as our, one second, this is our minus 2R dt, and so we substitute it, we get this as our Pdv, and this comes as minus 2R dt will be equal to 2R dt, and we can just combine these two terms. Therefore we get this as our P dv will be equal to 4 times R, and this comes as our dt. Okay, now we can easily find out our work done in the process. Okay, because work done is basically our PdV. Okay. So let us solve for our part A. So we can say work done in AB, which we can write as WAB, will be equal to our integration of PdV, and PdV is our 4R dt. Therefore, we can write this as our WAB is integration 4R derivative of T, and here our T1 is said to be given as 300 and T2 obviously will be equal to our 600. Okay. Therefore, we can say that our 600 to 300 will be our limit of integration with respect to our temperature. So this comes as 4R is our common, so this will be coming as our T. If we substitute, this will be 300 minus 600, and which will be giving us minus, this will be our 1200 times R. Okay, so this is the work done during the process of our AB. And part B, we have to find out heat absorbed or released in each of the processes. So basically we have three processes: AB, BC and CA. Okay. So let us solve it for our BC, and BC's pressure is our constant, so we can say it is basically isobaric process. So we can say part B and part B is our process is our BC, and this process is our isobaric. And isobaric, we can write that our QBC will be equal to N, and this comes as our C of P multiplied by our delta of T. Number of moles are our 2, C of P we know is our 5R upon 2, and the temperature difference is from 600 minus 300. Therefore, we get that our Q of so we get our Q of BC, and this 2 goes with 2, and this will be coming as 300. So 3 multiplied by 5 will be giving us as a 1500 times R. This will be 1500 R. Okay. Now we come to process CA. Process CA, and in this case the temperature is constant, so we can say this is isothermal. And for isothermal, we know that our change in internal energy, that is delta U, is equal to 0. And we can write using the first law of thermodynamics for QCA will be equal to our change in internal energy plus work done for CA, and delta U 0, so it doesn't matter. So simply we find out our work done, and that will be equal to our energy. So we can say our work done for our CA, which is our isothermal process, will be equal to N RT natural log of our pressure at C divided by pressure at A. And you can simply substitute the values. we get this as our WCA, N is our 2, R and temperature is our 600, and we have this natural log of our, this is our twice P1 divided by P1. P1 and P1 cancels out, so we get this as a 1200 R and natural log of 2. Therefore, we get our QCA, CA will be equal to 1200 R and natural log of 2. And now we come to our AB. Okay. And we can say our process is our AB, and for this process we can use our first law of thermodynamics, which say that Q of AB will be equal to our internal energy plus work done for our AB. Okay, and this internal energy will be our N C of V and delta of T plus work done of our AB, and WAB we already calculated. So this is quite simple now. So we get this QAB will be equal to 2 multiplied by C of V is our 3R by 2, and temperature difference is our 300 minus 600, and work done is our negative of 1200 times R. So here 2 and 2 cancels out, so this will be coming as minus of 300, so minus of 900 and minus of 1200. Therefore we can say that our QAB will be equal to minus of 900R minus of 1200R, giving us minus of 2100R. Okay. So this is our I think these are the only things which were required. Yeah. Okay. So we come to the next question. It was asked in the 2001, and it states that a monoatomic ideal gas of 2 moles is taken through a cyclic process starting from A as shown in the figure. The volume ratios are VB by VA is 2 and VD upon VA is 4. If the temperature at TA is 27 degrees centigrade, calculate. So based on this we have these 3 questions. Basic figure is given to us, so it start with A, move to B, then from B to C it is basically isothermal, and C to D our volume is constant, so this will be our isochoric, and then again it will be our isothermal for D to A. Okay. And we are given temperature at A is given to us, so TA is given to us, and the volume ratio for our various points is also mentioned to us. Okay. So basically we have monoatomic and we have 2 moles. So we can say that our number of moles, that value of N is equal to 2, and it is monoatomic, so therefore we can write that C of V is equal to 3 by 2 times R, and we can write this as C of P is equal to 5 by 2 times R. And we are given temperature at A, that is T of A is given to us 27 degrees centigrade, or we can say this has our 300 Kelvin. Okay, and we have to find out the temperature of the gas at point B. Okay, so their ratios are given, and the ratio is the common in both the ratio is our VA. So what we are going to do, we are going to assume that VA is our, suppose V naught, that is going to help us in find out our VB as well as VD as well as our VC. Okay. So we can say that let our VA is equal to V naught. Therefore, we can say that our VB will be equal to our twice of V naught, and our VD is 4 times V naught. Okay. And our VD and VC are same, so this will be also equal to our VC. So let us start with our process from A to B. Process AB. And in process AB, we can, if we see our, you can say this line, we can say that it is passing through the origin, and at temperature TA, volume is given as VA, temperature TB, volume is given as VB. So this, from here we can at least make an conclusion that our volume is directly proportional to temperature. So from here we can write it as our VB upon VA is equal to TB upon TA. Because we are interested in finding out TB, so we wrote the, you can say, the ratios in the reciprocal manner. And normally we would have written VA by VB and TA by TB, but it doesn't matter. And then from here we can write our TB will be equal to TA, and this comes as VB upon VA, and we simply substitute the values. TA is given to is our 300 Kelvin, and the ratio of VB by VA is 2. So we get from here the temperature at B is 600 Kelvin. Okay, so we found out option A is 600 Kelvin. Okay, now we come to the heat absorbed or released in each process. So we are going to, let's start with AB, then BC, then CD, then DA. So now we come to our part B, and part B we are once again going to consider process AB. And process AB, like we said, that our volume is directly proportional to temperature, or from here we can say that our pressure is constant. Therefore, we can write that for our QAB will be equal to NC of V and our temperature difference, that is delta of T. So this comes as C of V, not C of V, it's C of P. So this is N C of P, and we get this as TB minus TA. And we simply substitute the value. This is 2 and 5 by 2 times R, and 600 minus 300. 2 goes with 2, so we get our QAB will be equal to, this will be coming as 1500 R. Or we can say this is absorbed. Now we come to process BC. Process BC is our isothermal. And for isothermal, we know that our internal energy, change internal energy is equal to 0. Therefore, we can write that our this energy QBC will be equal to delta UBC plus work done for BC. This Q delta UBC is equal to 0. So simply we find out this work done and we can use the equation that our nRTB natural log of Vc by Vb, and we simply substitute the value. Number of moles is our 2 and R is our R, temperature is our 600, and this comes the natural log. Vc is our 4 times V naught and Vb is our 2 times V naught. So here this V naught and V naught cancel out. Therefore, we get this as our QBC will be equal to, and 4 goes by 2. So we come as 1200 R natural log of 2. R natural log of 2. Okay. And this is our also absorbed. Now we come to CD. Process CD, and in this process we have volume is constant, and volume is constant, so we know that our work done will be equal to 0. So we can say work done for our CD will be equal to 0. So if we use our QCD will be equal to delta of UCD plus W of CD, which is 0. So this comes as our simply change in internal energy. So we can write this as N C of V and delta of T. So number of mole is 2, C of V is our 3 by 2 times R, and the temperature difference will be equal to our 300 minus 600. And we get this 2 and 2 cancels out. So this will be our minus of 900 R. So we get this as QCD will be equal to minus of 900 R, and here it will be released. Now we come to the process of DA. And process of DA, once again our temperature is constant, so this is of isothermal, and for isothermal we know that our change in internal energy is equal to 0. Therefore we can write that our QDA will be equal to, this is for DA, internal energy change for DA plus work done for our DA. Internal energy will be 0, so we can use the work done equation directly, and that is given as nRT of D natural log of our VA upon VT. So we substitute the values, we get this as QDA will be equal to 2 times R, TD is our 300, and VA is our V naught, and VD is our 4 times V naught, and this V naught cancels out, so this comes as 1 by 4. 1 by 4 we can take in the numerator, so this comes as minus, and this will be our 600 R natural log of 4. So this will be also our released. So these were the part B, and it says that total work done by the gas in the complete cycle. Okay, the total work done will be the addition of the individual work done. So we can say our part C. Part C, we can say that our for complete cycle we know that our net change in energy for the entire cycle will be equal to 0. Therefore, we can write that our work done total will be equal to our energy of AB plus energy for BC plus energy for our CD plus energy for our DA, and we substitute all these values. We get this as our 1500 R, QBC is our plus QBC is our 1200 natural log of 2 plus QCD is minus 900 R and this comes as minus. We can write this as in the natural log of 2, this will be also coming as 1200 R natural log of 2. Okay. And these two terms cancel out, so we get this as our total work done will be equal to 1500 R and minus 900 R, giving us 600 R. So this is the total work done. Next question. It was asked in the year 2001, and it states that an ice cube of mass 0.1 kg at 0 degree centigrade is placed in an isolated container which is at 227 degree centigrade. The specific heat S of the container varies with the temperature T according to the Ampere relation S is equal to A plus BT, where A is 100 and B is 2 into 10 to the power minus 2. If the final temperature of the container is 27 degrees centigrade, determine the mass of the container. The latent heat of the fusion of the water is 8 into 10 to the power 4 and specific heat of water is given as 10 to the power 3. So in this case, we are given that there is an ice cube which is kept in a container. Okay, and its temperature varying equation is given to us. So obviously you can say, because the final temperature is said to be given as 27 degrees centigrade. So because of this, there will be some heat gained by the ice. Then only the temperature is going to drop. Okay, and it is basically isolated container. Therefore, we can say the heat lost by the container will be the heat gained by the ice. So it means no loss of energy, heat energy is going to take place. So let us write the things which are given to us. We are given our ice cube, so we can say our mass of ice, let us call this as M of I, is equal to 0.1 kg, and it is a temperature of 0 degree centigrade, or we can say 273 degree Kelvin. And the final temperature is said to be as our 27 degree centigrade. So we can say ice melts and final temperature, let us suppose this is T of F, will be equal to 300 Kelvin, and the initial temperature of the container is given as 227 degrees centigrade. So we can say container initial temperature let us call this as TCI, will be equal to 227 plus, so it will be over 500 Kelvin. And rest of the things are quite simple, need not to go into the details. So first of all, we are going to find out, okay, and isolated system is there, so we can say that we are having isolated system so from here we can say heat lost by the container is equal to heat gained by the ice. So let us first of all find out the heat gained by the ice. So first of all, the ice is going to melt. So we can say the first part for this, in the process of this ice, we can say the ice melts and in this process, let us suppose the heat is called as our Q melt, which will be equal to its mass of our ice and its latent heat. So we get this as 0.1 into 8 into 10 to the power 4, and this comes as our 8000 calorie. Now the final temperature is our 27 degrees centigrade. So now the water temperature is going to rise from 0 degree centigrade to 27 degrees centigrade. So that will be our second step. And we can say that warm water from 0 to 27 degree centigrade, and let us call this as Q warm, and this Q warm will be equal to our mass of ice, specific heat of water, and our temperature difference. So we simply substitute the value, we get this as Q warm will be equal to mass of ice is about 0.1 and specific heat of water is given to us as 10 to the power 3, and temperature difference is our 0 to 27 degrees centigrade, so this will be our 27. Okay, and not degree, in Kelvin also the difference will be 27. Okay, so therefore we get this will be equal to as 2700 calories. Okay. Therefore total heat gained by the ice, which we are supposed calling as Q ice, so Q ice will be our Q melt plus Q warm. So we can say our Q ice will be equal to Q melt plus Q warm. and Q melt is about 8000 plus Q warm is about 2700, and this comes as our 10700 calorie. Now we find out the heat lost by the container, and in this case we have to remember that the specific heat of the container is based on this empirical equation, okay, which is basically temperature dependent. Okay, as the temperature is going to change, the specific heat is also going to change. So we can say that our heat heat lost by the container and let us call this as our Q container will be equal to our mass and equation of a specific heat, that is A plus Bt d of T and its integration for our final temperature and temperature of our TCI. Okay, and TCI is our initial temperature of our container, which is about 500 Kelvin. Okay, and this we can just solve it. We get this as our mass is our m, and we get this our A of T plus Bt square divided by 2, and integration will be from our 300 to 500. Okay, and if we substitute the values, which will be quite easy, and we can say m, and we have this as, this will be our 500 minus 300, that will be A multiplied by our 200 plus B by 2, and this will be our T square, that is 25 minus 9, that will be 16. So it will be coming 16 and 1, 2, 3, 4. Okay. And we can, this goes by 8, 1, 2, 3, 4. So we can say that our okay, A and B are also given to us. So we can write this as our M, and A is given to us as 100. This comes as multiply by 200 plus B is given to us as 0.01 and multiply by 0.01 or 0.02. B is 2 into, so this is 2, and multiply by our 80,000. And this entire thing, let me write directly, this will be coming as 216,000 times M. Okay. And now we can equate heat lost by heat gained. Okay, that was our initial hypothesis. So we can say that our heat lost is equal to heat gained. Therefore, we can write that our 216,000 times M will be equal to 10700. So from here we get our M will be approximately equal to 0.49 kg. Okay. what was asked for? Mass of the container was supposed to calculate. Okay. Next question. It was asked in the year 2002 and it states that a cubical box of 1 meter contains helium gas, atomic weight 4, at a pressure of 100 Newton meter square. During an observation time of 1 second, an atom traveling with a root mean square speed parallel to one of the edges of the cube was found to make 500 hits with a particular wall without any collision with other atoms. Take R as 25 by 3 and value of K is 1.38 10 to the power minus 23. So based on this, we are going to find out these three things. First is our temperature of the gas. Okay. And so let us start with part A. Part A is our temperature of the gas. So first of all, we are given that the atom is traveling with a speed of a root mean square speed. So we can say that an atom traveling from root mean square. Okay, so we can say that cubical block side is our 1 meter. Okay, so let us say that length of box L is given to us as 1 meter, and so in this case we can assume that suppose this is our x-axis and this is our y-axis, and the container is placed such that one of the edges is at the origin. Okay, so this is our total length, that is given as L is equal to 1 meter. So obviously this equation will be equal to x is equal to 1, and it starts from x equal to 0 and strike at x is equal to 1. So therefore the total distance it will be covering in one round trip will be equal to twice of L. Okay, so it is going to travel to our right side first, hit the wall, and then it will be coming back. Okay, so the total distance will be 2L. Therefore we can write that time for one round trip, time for one round trip, and let us suppose that is given as t, and we can use the basic equation that t is equal to distance oblique speed. Total distance will be over 2L, and speed is in x direction, it is traveling this direction, so we can say this is v of x, so this will go v of x, which comes as our 2 upon and v of x. So this is the time taken, and we are given the frequency of hits is given to us, so we can say frequency of hits, and which is basically, we can say that hits per second and that hits per second will be equal to, in this reverse of this time period, so we come this as our Vx upon 2. So this is our frequency of hits, and this frequency of hits is given to us as 500. Therefore we can say that our V of x will be equal to 1000 meter per second. Okay. Now, but it is said that the velocity is root mean square velocity. Okay, so we only know our V of x, and we can find out the root mean square velocity. Okay, so next is our we are given that atom travels with root mean square velocity parallel to one of the edges where it is x-axis. Okay, so if we write the equation for our VRMS in terms of all the three coordinates, okay, therefore we can say that our VRMS will be equal to our Vx square plus Vy square plus Vz square and its square root. And since we know that our gas is isotropic, so we know that our gas is isotropic, therefore the mean square velocity will be equal in all direction. Therefore we can say the mean square velocity is equal in all direction. So based on this we can just write that our Vx square will be equal to Vy square will be equal to our Vz square, and that we can write as 1 by 3 and our V square, or we can simply write it as V square RMS divided by 3. Thus we can say that our here VRMS and from here we can write this as our VRMS upon square root of 3 will be equal to Vx, and let me write it in the form of square root. Okay. But in the question it specifically mentions that the atom travels with a root mean square velocity speed in only one direction. Okay, so we can say as per question atom travels in only one direction, which is positive x, in only one direction. Therefore we can write that our V of x will be equal to our VRMS, okay, and which will be giving us as 1000 meter per second. And okay, we have to find out temperature. Now we know VRMS, we can just find out the temperature, the basic relationship. So we can say that our VRMS is equal to 3RT upon M square root. Okay, R is given to us, VRMS we know, temperature we can easily find out. Therefore we can write that our temperature T will be equal to VRMS square and multiply by M divided by 3 times R, and we substitute all the values. VRMS is our 1000, so this comes as our 1000 square, multiply by mass which is 0.004, this is 3, and R is given to us as 25 upon 3. So here 3 and 3 cancels out, so we get this temperature will be equal to 160 Kelvin. Now we come to our part B. Part B states the average kinetic energy per atom. So we have our part B, and which is based directly on the formula that our average kinetic energy per atom, let us suppose we write this as E of K is equal to 3 by 2 K times T, and we already know all these. K is given, temperature we found out, therefore we can write that our E of K is equal to 3 by 2 multiply by K. K is our 1.38 into 10 to the power minus 23. Temperature is our 160. So this comes approximately as 3.312 into 10 to the power minus 21 joules. Okay. And finally, the total mass of the helium in the box. Okay. So we can use our ideal gas. From there we are going to find out number of moles, and then we can find out our total mass. So part C, we are going to use ideal gas equation. That our PV is equal to nRT, okay, and our N will be equal to PV upon RT. So we substitute it, we get this as our 101, and R is our 25 by 3, and temperature is our 160, and this comes as 300 divided by, so the number of moles we can put, this will be equal to our 0.075 moles, and total mass that is our M total will be equal to number of moles and the, we can say, given mass, that is M. Number of moles is 0.075 and M is given as 0.004. So we get our total mass will be equal to 3 into 10 to the power minus 4 kg. Next question. It states that it was asked in the year 2003, an insulated box containing a monoatomic gas of molecular mass m moving with speed v0 is suddenly stopped. Find the increment in the gas temperature as a result of stopping of the box. So here basically it is moving with some energy, that will be our kinetic energy, and then we can use that for our calculation. Okay. So first of all, let's find out the kinetic energy of the gas. Kinetic energy of gas, and let us call this as E. Gas will be equal to our half mass of the gas, and its velocity is V0, so this comes as V0 whole square. Okay. And molar mass is given, so if N is the number of moles, therefore we can write this as our E of gas will be equal to 1 by 2 number of moles multiplied by molar mass, and we have this as V0 square. Now this, all of a sudden, this energy will be dissipated into internal energy. Okay. You can say this is our, you can say, dissipated into internal energy. And we know our internal energy is nothing but with respect to temperature. So we can say heating of gas. Heating of gas. Okay. So let's find out the internal energy, and that is directly based on the formula itself. We can say that our internal energy will be equal to N C of V, and we have this is delta of T. So we can write this as our N, and this comes as 3 by 2 R because it is monoatomic, times R and delta of T. Now we can use conservation and get the answer. So we can say that our E of gas will be equal to our delta of U. So we get this as 1 by 2 N times M V0 square is equal to N 3 by 2 R and delta T. Here N and this 2 cancels out. We get our delta T will be equal to M V0 square upon 3 times R. So this is our rise in the temperature. Next question. It states that the top of an insulated cylinder container is covered by a disc having emissivity of 0.6 and conductivity of 0.167, thickness of 1 centimeter. The temperature is maintained by circulating oil as shown in the figure. So based on this, we have two questions. Part A, find the radiation loss to the surrounding if the temperature of the upper surface of the disc is 127 degrees centigrade and the temperature of the surrounding is 27 degrees centigrade. And part B, also find the temperature of the circulating oil, neglect the heat loss due to convection. So basic figure is given to us. So we are giving a cylinder and top is covered by a disc, and we have the input of the oil and output of the oil. Okay. So first we are going to find out its part A, the radiation loss to the surrounding. Okay. So first of all, let's write all the things which are given to us. First of all, we are given as emissivity. That is our E is given as 0.6. then we are given that the temperature, disk upper surface temperature, so it means this upper surface, one second, upper surface I think must be this one, and the surrounding is our this top one. So we can say that disk upper surface temperature, disk upper surface temperature, let us call this a TS, is 127 degrees centigrade, or we can say this as about 400 Kelvin. And we also have temperature of surrounding, so we can say surrounding temperature, and let us call this as T infinity, which is about 27 degrees centigrade, or we can say 300 Kelvin. And conductivity is given, rest of the things doesn't matter. Okay, and it is given that the radiation is, or we can say we assume that all the radiation loss is from the top surface. Okay, so whatever losses are going to take place is from the top surface only. Okay, not from the other part except the heat part through the oil. Okay, so first of all, let's find out the radiated heat loss per unit area. So we are having radiative heat loss per unit area, and for that we can use our Stefan-Boltzmann law. Stefan-Boltzmann law, which gives us that I will be equal to E and rho multiplied by our temperature difference, that is T of S whole raised to power 4 minus T of infinity whole raised to power 4. Okay. And we substitute the values because everything is given to us. So we get our I, emissivity is our 0.6, and this sigma, which is our Stefan-Boltzmann constant, is our 5.67 into 10 to the power minus 8, and temperature of the surface is 400, so this comes as 400 whole square minus 300 whole square. So we get our I will be approximately equal to 595 watts per meter square. Okay, and this was our radiation loss for this. Okay, and okay, now we come to the part B. And part B, we have to find out the oil temperature, and oil temperature, and for that we are going to assume that it is a steady state condition and the loss is entirely radiation loss. Okay, so we can say this is steady state condition and entirely loss is our radiation loss. And because of this circulation of oil. First of all, let's find out the okay, let us say the heat flux by conduction one second. Okay, convention is neglected. So heat flux by conduction through the disk per unit area. And let us call this as Q conduction, that is equal to our K temperature of oil minus temperature of our upper surface and divided by L. Okay, here L is nothing but our thickness of the disk, okay, which is given to us as 1 centimeter. And at steady state, we can say this Q conduction will be equal to our I, and we substitute it, we get our I will be equal to K times T oil minus T of S divided by L. So from here we can write our T oil will be equal to, this comes as our IL upon K plus TS, and we already know all these values. So we plug in the values, we get T oil will be equal to I, we found out is our 595 multiply by our thickness 0.01 divided by the constant which is given as 0.167 and plus surface is given to us as 127 degrees centigrade. So from here we get our T of oil will be equal to approximately 162.6 degrees centigrade. I think this was the last one. Yes. So this completes all the 6 questions. Thank you.